In this video, we're going to derive the polar form of the Cauchy-Riemann equations. So recall a few things first. Let's let A be some subset of the complex plane. And let's let f be a function whose domain is A, where f of z has real part u of xy and imaginary part v of xy. So again, remember a complex valued function, it too has a real and an imaginary part just like a complex number does. And each of these are real valued functions, functions of two real variables, that is also. And just in case we're not clear here, z is an element of the domain, so it's a complex number you plug into the function. You know, z has its own real and imaginary part, say x and y, so z looks like x plus iy, where x and y are real numbers. Now, a necessary condition for this function f to be complex differentiable at a particular complex number z naught, say x0 plus I y0, is for the function f to satisfy the Cauchy-Riemann equations at your point you're interested in, z naught. And to remind you, what are the CR equations? It's the system of two partial differential equations where the partial of u with respect to x at your point has to be the same as the partial of v with respect to y at your point, and the negative of the partial of u with respect to y at your point has to be the same as the partial of v with respect to x at your point. So the CR equations in rectangular coordinates, in other words with respect to x and y, you might kind of shorthand them like ux equals vy and minus uy equals vx. I'll try to be more careful to, when using these subscripts like this, that denotes partial derivatives, so I'll try to be more careful to say partial u of x, and partial is the same thing as partial v with y, and minus partial u with y is the same thing as partial v with x. But just in case I ever slip up, just hopefully we're clear on what these symbols mean. Now here's a question. What do the CR equations look like if you use polar coordinates instead? And like rectangular coordinates, x and y are cool, but we know that polar coordinates are another fine way to describe points in the plane. But just for a very quick refresher, what are polar coordinates and how are they related to rectangular coordinates? Remember, polar coordinates, we're using circles centered at the origin in order to try to describe points in the plane. And the relationship here between the polar variables r and theta with the rectangular variables x and y are the following. So r is the square root of x squared plus y squared. Theta is equal to arctangent of y over x. And other formulas that are useful are x is equal to r cosine theta and y is equal to r sine of theta. So these four formulas help me switch back and forth between the two sets of coordinates, polar coordinates and rectangular coordinates, that is. Now suppose that we have a complex valued function or a function of a complex variable, f, and it's got, real part u and imaginary part v, and let's say that f satisfies the CR equations. So partial ux is partial vy and minus partial uy is partial vx. What are the partial derivatives with respect to polar coordinates? How are they going to relate to each other? So we should try to get some formulas for partial ur, partial u theta, partial vr, and partial v theta. And we're going to obtain formulas for those by using the chain rule from Calc 3. And so how do we figure out what does partial UR look like? And you might remember from Calc 3, you typically made some kind of like a little tree or molecular diagram, depending on how you learned it, where I put the dependent variable u at the top, x and y are like the intermediate variables, and I care about the independent variable being r. And in a minute, we're going to do theta too. So those go on the bottom. And the question is just how can I start at the top u and work my way down to r? Well, one way to do that is to go from u to x to r. And the way I'm going to write that is partial ux times partial xr. And then another way to do it is to go from u to y to r. So we have plus partial uy times partial yr. And I know what the formulas for x and y look like, so I can take those partial derivatives with respect to r, so that those partials just turn into cosine theta and sine theta respectively. So we've obtained a formula here for what does the partial of u look like with respect to r. Similarly, I could figure out what does the partial of u look like with respect to theta. We just want to go from u down to theta with our tree, so in a similar manner you could get partial ux times partial x theta plus partial uy times partial y theta. Same thing, you've got formulas for x and y up here, just in case you forgot, and you can take those derivatives with respect to theta. So those would look like, well, partial x theta looks like minus r sine of theta, and partial y theta looks like r cosine of theta. You can play the same game with v, and it's going to look very similar, we're just going to get partial Vx times partial xr plus partial Vy times partial yr. And, the same derivatives, you're going to use them again. So xr becomes cosine of theta, and yr becomes sine of theta. And partial v theta looks very, very similar as well. And so what we want to do is we're going to try to compare some of these expressions to each other. The first two we're going to compare to each other are UR and V theta. And so maybe just for a moment, look at the formulas for UR and V theta that we just derived, and let's go for it. So here's the formula for UR, and what we're going to do is we're going to invoke the Cauchy-Riemann equations that we know for rectangular coordinates. So I know that UX can be replaced by VY, and I know that UY can be replaced by minus VX. And so what do we get? So if I do those replacements there, what we're going to try to do is we're going to try to see if we can get V theta to show up. So that's maybe my rationale for why I'm using the rectangular Cauchy-Riemann equations in this way. So now I'm just going to try to do some algebra to try to see, well, how can I get this to look more like V theta? So how does this formula I have compare to V theta? And one thing that I'll do is I know that, the thing with sine, if you look up at the formula for V theta toward the top, the sine part's negative, so I'll just go ahead and write that one first. And then I've got Vy cosine of theta, and it looks like the only thing I'm really missing is an r. If I can get an r into the picture, that's great. So I'll do one of our favorite tricks, which is to multiply by 1 in a sneaky way. And when I do that, I'm going to write 1 as r over r, and what I'll do is I'll distribute that top r through so that it looks exactly like my formula for partial V theta up at the top right. And when I do that, I get 1 over r times partial V theta. Now we're going to compare partial U theta with partial VR. And so again, if I go up here, we're going to compare partial U theta with partial VR there. So go ahead and look at the formulas for a second. See if you can work through this also. And the way I'm going to do this is I'm going to start with the formula for partial U theta. And again, see if I can try to manipulate this so that it spits out partial VR. So here is the formula for partial U theta. We're going to use the rectangular Cauchy-Riemann equations in the same way. I want to change these partial ux and partial uys to partial vx and partial vy's. And so we change it in the exact same way. And now I'm just thinking about what do I need to do to this expression that we just obtained in order to make it look like the formula for partial vr up toward the top left right now. So we're pretty darn close. It looks like we've just got to factor out a minus sign, and we could factor an r off of those as well. And what we obtain then is this is minus r times, we have r partial VR. So thus we get the CR equations in polar form. They look like partial UR is 1 over r partial V theta, and partial U theta is minus r VR. We know that in rectangular coordinates, the derivative of my complex function f, so f prime, it's the partial derivative of the real part with respect to x plus I times the partial derivative of the imaginary part with respect to x. So what does f prime look like in polar coordinates? So we've got a good expression in rectangular coordinates. What's the corresponding expression look like in polar coordinates? Again, we're going to use the chain rule, but we're going to flip-flop who the independent and intermediate variables are. Now notice r theta is in the middle and xy is on the bottom. But what we can do then is we can rewrite the partial of u with respect to x. If I use my tree diagram, that's the same thing as the partial u with respect to r times partial rx plus partial u theta times partial theta x. We have formulas for r and theta. So if I scroll up, here are my formulas for r and theta, and I can take partial derivatives of those with respect to x or with respect to y. And so if I scroll back down, what does this look like? So this looks like UR. Now the partial of r with respect to x, we're differentiating that square root. And so we use the chain rule, right? The 2x's from the chain rule of the x squared inside. And then plus partial u theta. And then we got to take the derivative of arctangent of y over x. And so again, that's a chain rule problem too from Calc 1, or maybe Calc 2, depending on when you learned about arctan. Anyway, there is the formula for those derivatives. And now what we're going to do is a little bit of algebra to clean this up. Believe it or not, it's going to simplify very nicely. I'm going to go ahead and write the square root in that first part in the bottom, and I have an x up top. And what else do I see? I can make that fraction that came from the derivative of arctan a little bit nicer by multiplying everything by x squared in the top and the bottom of that fraction. And I see now that the x squareds are going to cancel there. And what else do I see? Let's go ahead and change to polar coordinates. So, well, x is r cosine of theta. Square root of x squared plus y squared is r. And over on the other part of the sum here, remember the x squareds cancel, so I just have minus y in the numerator. But that's the same thing as minus r sine of theta. And then x squared plus y squared without a square root, that's r squared. And so just simplifying a little bit more, I see the r's cancel, or some of the r's cancel anyway. So I get partial ur times cosine of theta minus sine of theta over r times partial u theta. The partial of v with respect to x is going to be really similar. And the good news is we already computed rx and theta x. So I know that those just work their way down to cosine of theta and to minus sine of theta over r respectively. So we don't have to go through all that calculus again. So what do we just do? We just obtained formulas for ux and vx. And so by the above, the derivative of my function f should just be, what do you get when you add these expressions together? And so let's go ahead and do that. So we will substitute in what we just found each of these to be. So here is what ux is. And now I have plus I times here is what vx is. And you might be wondering, what have I colored? Why are those an orangish color? I'm going to use the polar form of the CR equations here to manipulate these a little bit. So what we uncovered earlier was that, well, minus u theta over r is vr, so we can do that swap in the next step. And then ur is the same thing as v theta over r, so we're going to swap that out in the next step as well. Now if we continue going through this here, all we're going to do is we're going to rewrite this a tiny bit. Let's try to get the UR terms together, and let's try to get the VR terms together. And so again, if you think about maybe distributing and then refactoring in a way so that the UR terms and the VR terms are kind of separated, this is what you should obtain. And just a little bit of algebra we're going to do is these formulas look fairly close to each other. And what we're going to try to do is, can I get a cosine theta minus I sine of theta in the right set of parentheses too, in which case I could factor it out. And I can. What I'm going to do is I'm going to factor an I out of everything I see on the right side there. And so when I pull an I out, obviously it comes off the cosine. But again, when you factor out I from just sine of theta, you're thinking you have an I in the denominator. But remember, an I in the denominator is the same thing as minus I. So again, just some tricky algebra with I there. But why is that good? Now if you compare what's inside both sets of parentheses, they match, so that you could factor that term out front, and we obtain the expression for the derivative of my function f in polar coordinates looks like partial ur plus I times partial vr times cosine of theta minus I sine of theta.